Okay, partial fraction decomposition. So if q is a rational function, then q of x can be defined by f of x divided by g of x, where these are just polynomials. Alright, we will state rules for evaluating the integral of q of x dx, but first of all, let's just look at a little example. If I have 1 over x minus 1 plus a negative 1 over x plus 1, this is just the partial fraction decomposition of this right-hand side. So on the next page, we'll look at how to evaluate that using partial fractions. Okay, so here we can see to evaluate the integral of 2 over x squared minus 1 dx, we can integrate each of the fractions in the decomposition. So from the previous page, we have this one plus this one. So let's go ahead and evaluate that. And when we evaluate this term right here, we're just going to get the natural log of x minus 1. If I pull this negative out, I'm just going to get a negative here, and this one will give us the natural log of absolute value of x plus 1. And then, of course, we have plus a constant, right? Now, because both of these are log, we can reuse our properties to rewrite these. What would we do to rewrite subtraction if we wanted to take this a step further? We can condense these to the natural log of x minus 1 over absolute value of x plus 1. And then remember our plus a constant. So we can remember our logarithmic properties there. Also, we want to make a note that the degree of the numerator must be less than the degree of the denominator. In this case, it is. Okay, so that just sets everything up. And before we actually get started on our examples, recall that if I have, let's just go back very basic, 1/2 plus 4/5, right? Let's just do that. If I wanted to get a common denominator, what would my common denominator be? Good, we can just do 10. So if I just set it up like this, what would I need to multiply 2 by so that I can get 10? 5, right? So let's just say if I said, let me put in parentheses, times 5, whatever you do to the denominator, you must do to the numerator as well. So then that would just change this to 5/10. And then over here on this second fraction, what do? We multiply this by 2. So just way back, we're going way back, I know, but hopefully this simplifies things a little bit for you. So that would just give us this. Now that they have a common denominator, we can add across and get 13/10, right? Okay, so keep that process in mind as we move forward with these first examples. Okay, so ultimately we're going to be using partial fractions when the degree of the numerator is less than the degree of the denominator. In the case that it's not, we would use long division. But what I'm going to do is I'm going to just pretty much take you through some examples first, and then at the end I'm going to wrap this up into specific cases, in which we'll have 4 cases. So we're going to just work through the examples, and then I'll label each of the cases. Okay, so the first thing we're going to do to start this is factor the denominator. So we'll have 3x plus 1. And then what would our denominator factor to? Trinomial. What multiplies to give us 3 adds to give us 4. X plus 3, x plus 1, right? Alright, so the idea in partial fraction decomposition is we want this to be the product of 2 terms like we did before. So basically what we're doing is we're starting with this side and we're trying to rewrite it into this format. So our first step is we factor, and now we would like it to be sum A, which we're going to have to determine in a minute, over x plus 3, plus B, which we're going to have to figure out, over x plus 1. Okay, so in our note is we need to figure out A and B so that these are equivalent, that when we actually add these, get a common denominator and add these, that it will be equivalent to this. Okay. Okay, so our next step is going to be to actually take these two which separated apart and get a common denominator. What would be a common denominator for both of those? it would just be the x plus 3 times the x plus 1. Okay, now what do I need to multiply this by so that I have this entire denominator? X plus 1. So I'm going to have a, and let me put it in a different color so we'll see. And that's why I did that baby fraction before. I know that was way below your level, but just want you to see. All right, for this term, if I have x plus 1 already, what do I need to multiply it by to get the denominator? X plus 3, so I'm going to just put that in a different color. And we won't take such baby steps through this entire video, but just to get you started. All right, now what we want to do is, if I was to carry this down, we can see that they're equivalent, but I just want to focus in on the numerator. So I would say this 3x plus 1, which is my numerator, is equal to the numerator on the right-hand side, which is ax plus 1 plus bx plus 3. So we zone in on our numerator because we are looking to figure out the a and b values that can make this valid. So let's go ahead and I'm just going to carry this down. Let's distribute this out. Ax plus a, bx plus 3b. Now if you remember grouping, the first thing we're going to do is we're going to group our x terms. So in this case, this term has an x in it and this term has an x in it, so we're going to put those next to one another. So right now I'm just going to group. So it's going to be ax plus bx, and then what's left is just going to be a plus 3b. And all we did was rearrange and regroup. Okay, now can I factor out an x right there so that I just have a plus b x, right? So factor that out. I'm just going to leave this other side alone right now. And after we've done a few of these examples, this will start to feel a little more comfortable to you. So as we're going to be setting this up, what does the a plus b equal in respect to this left-hand side? Let me get a highlighter here. So a plus b is going to be equal to our 3, right? Okay, so we can set that up. Let me see if I can extend page. And what about this 1 is equal to everything that's left over here, right? So we're going to set those two up. Let me extend my page a bit. So what I have now is I have a plus b is equal to 3. And I also have a plus 3b is equal to 1 by that given information. Okay, so that the format matches. All right, what can I do with these two? That's a system of equations, right? System of equations. So I'm going to rewrite that. Okay, so if I set them up, I'm going to solve this system of equation. What I want something to eliminate. I can work with the A's, or I can work with the B's, and there's lots of options here, but I'm just going to go ahead and try to get the A's to cancel. So I can multiply this top one by a -1, right? That's one option. And if I do that, that would just give me -a, -b equals -3. I leave the second one alone, a plus 3b is equal to 1. What happens with the a's? They cancel. In elimination, that's what we're trying to do. It doesn't matter if you chose to eliminate a or b, or how you chose to do it, as long as that's the case. Then in this situation, we'll have 2b is equal to -2. Solving for b, we find out that b is equal to -1. Now, once I know b, what can I do? I can go back and plug it into either one of these, and it doesn't necessarily matter. So I'm going to substitute. So I'll say, let me go into a plus b is equal to 3. A minus 1 is equal to 3 because I plugged -1 in place of b right there. Add 1 to both sides. and a is going to be 4. Now, ultimately, remember we come back up here and we needed to figure out a and b. Well, now I know a and now I know b, and I can plug that back into this. So that would just give us, we could say our original 3x plus 1, original q of x, x squared plus 4x plus 3. The partial fraction decomposition of that will be 4 over x plus 3 minus 1 over x plus 1. And we're going to just break that down right there and stop. So what we did there is we took it, we factored it out, we put it over in a and a b, and then we used this method to determine what a and b was so that we can rewrite it. Okay, now if we was asked to integrate this, we could do the integral of this minus the integral of this just like we did before and break things down so that if you have something really complex, sometimes this is a method we'll use to break it down and simplify it a little bit.